So for tomorrow, I will try to do the same because I think that otherwise you will not be able to start recording. So I would just try to join, but without a microphone and without a camera, because I will be leading the Warsaw AI meetup at the same time. So this can be interesting.
Right.
Okay, you are the host now. Good luck.
Yes, I can share. Thank you very much. Okay, hello everyone. Today is the third day of our lectures. Yesterday we did Deutsch-Josa algorithm and Barnsley-Vazirani algorithm, which still were Oracle-based algorithms, which took some specific problems and provided solutions which were significantly faster. Now, these problems don't have that much application in other problems that are important to our physical world. But I think they're very good to show what we can do with quantum algorithms, just the potential. Today we'll be discussing Simon's algorithm, which is a more important algorithm, which was the inspiration for Shor's algorithm, which I think I will talk shortly about in a bit. And this is the only notebook for today, so I am expecting us to finish early. And yes, this will mark the end of the conventional quantum algorithms part. And tomorrow we'll start the part about the max cut problem being solved with Grover's algorithm. We can get right to it. Yes, I can talk about this now. In case of Simon's algorithm, it's part of a special group of algorithms that are called hidden subgroup problems. I will talk about it a little bit later, but in many of our cryptographic systems and systems which provide security to our banking accounts and to other important information, there's an algorithm that's called RSA, and it's based on multiplying two very large prime numbers. Why? Because one of the harder problems that we have is, or rather, it's in the group of our algorithms which are very hard to find a solution for. And it's factoring. So trying to find prime numbers that by multiplied form that number. And why am I talking about this? Because this is one of the biggest, if not the biggest, achievements of quantum computing so far, is Shor's algorithm. And it's also for factoring numbers. Now, I will not say how or why, but it could potentially break RSA. There's been a lot of talk about this. Breaking RSA would mean the lack of security in like in most of our systems around the world in some way. So far, the caveat is that we don't have enough qubits, essentially, because the number of qubits can scale exponentially, and you can add qubits easily to a quantum computer, but the more you add, the more errors you'll get. So that's the short answer to why we still have RSA working. And so that's just important because I would say it's the most well-known algorithm. Here I also would highly recommend the QSilver workshop that's also done by QWorld. It goes through Shor's algorithm in great detail, and well, you can understand exactly why it works and why it is that much faster. But yeah, Simon's algorithm was the inspiration for Shor's algorithm. I think that's an interesting and useful fact to know. We can see what the problem is. It calls the Simon's problem. It could be a bit similar to Bernstein-Vazirani algorithm that we were talking about yesterday. So we're given a function which is implemented by an oracle, which will map n-bit strings to n-bit strings. We were mapping n-bit strings to um, 1-bit strings earlier. Now it's n to n. So for example, for n equals 3, we'll have being mapped to, say, 101, etc. And the function has a property where f of x is equal f of x or some s. And s is the secret message that we want to find, similarly as in Bernstein-Vazirani. And s is also a sequence of n bits. So we want to determine the value of s, making as few queries to f of x as possible. Now, we already did what bitwise XOR is. I hope you remember it. Essentially, we just need 1, 1 and 1, 0 to get a 1. Otherwise, you get 0. So if the two inputs are the same, we get zeros. If they are different, we get ones. Now, if we have a random bit string R, where R is also a sequence of n bits, and the 0 string Z, this will return the R as the output, which is a bit of a generalized notion that we were using to prove one of the tasks before, if you remember. If not, that's okay. We'll have a similar task here. So now, just to see how it works, we have n equals 3, and we have 4 a's. And let's go through one of the examples. So 101 XOR 011. And in this case, it's just showing us how to do it on multiple bit strings. We're just using XOR for each of these coordinates. So 1 XOR 0, which will be 1, 0 XOR 1, which will also be 1, and then 1 XOR 1, which will be 0. This is how we'll be operating on the n-bit strings. Now we understand the XOR. We remember a bit about the S secret message. So now we will investigate an example of a function that has the property that we are talking about. Now, let's start with thinking about what the function is. And this function, if S is not 0, is a 2-to-1 function. which essentially means that we get one output for two inputs. Let's check, for example, let's check 0, 0, 1. Okay, we have 0, 0, 1. That's X, that will be the domain. And that's the range. So we're mapping it to 0, 1, 0. And let's look if we have any other 0, 1, 0 in here. Or count how many more. We have one here and no more. And we cannot have any more because this is a 2 to 1 function. And that's for 1, 0, 0. So let's calculate what is going on. If X is 0, 0, 1, and S, which also can be called a mask, that is something that we don't know, but we are given in the example that I'm supposed to show you. So we just know what it is, but we want to see how exactly it works and investigate how f of x will behave. So f of x is 0, 1, 0. Now, x or s is 0, 0, 1, XOR 1, 0, 1. Here, 0 and 1, so we have 1, 0, 0, so we have 0, 1, 1, so we have 0. Now, what is the 1, 0, 0? Well, it is the other input that we have to generate this output. We can write it like this. So fx XOR s is equal to f1, 0, 0. And that's 0, 1, 0. That's one example. Make another one. Should be visible. So now we can check 0, 1, 0. We get 0, 0, 1. Now, where do we get another 0, 0, 1? It's here for the input 1, 1, 1. And let's see if it works as well as the first example did. So x is equal to 0, 1, 0. S is equal to 1, 0, 1. So f of x equals 0, 0, 1. X XOR s is equal to 0, 1, 0, 1, 0, 1. And this will be 1, 1, 1. Meaning that f of x XOR s is equal to f of 111, and that's 0, 0, 1. And you can check, for other ones. I would recommend checking just at least one pair like this. For example, you can try to check the 0, 1, 1 and 110, just for a better understanding. Now, we have our first task. We have the above function here. Well, yeah, it's for checking the rest of the bit string. So I would like you to check just this one in a similar way. I think, well, we can have 5 minutes for it since we'll have some more time. All right, let's check. So our x will be 0, 1, 1. X, x or s will be equal to 1, 1, 0. f of 0, 1, 1 is the same as f of 1, 1, 0. And that's 1, 0, 0. And thank you, Mark, for the answer. I think it's correct. I'm not 100% sure about the notation, but I think it's good. We can proceed further. Now, we
I
want
use
to
the
make
Python operator.
Right, okay. I see, thank you.
Thank you.
So we want to make as few queries as possible, of course. And if s is not the 0-bit string, as I said, the function is 2 to 1. So that's if we have two inputs, if we find the two inputs x1 and x2, which yield the same output, then x1, XOR x2 will give us our secret string s. So that's important. Meaning, if you had a classical solution, this is the only way, really, like this is the basic way, let's say, that you would look for it. You would need to find two inputs which yield the same output, which you can already see might be difficult in the computational sense. Immediately we have the second task. It's similar to a proof we've done, I don't remember, maybe Deutsch algorithm or Deutsch-Josa. But we're given the function which satisfies the property of the Simon's problem, and we need to prove just what we saw here. So if we have x1, XOR x2, then it will yield s. If, of course, the outputs are the same. So this can also be just a one-line proof if you remember associativity and what two of the same inputs applied to the XOR function give us. So for this also 5 minutes. Let us check. Well, we're giving again two inputs that yield the same output, and we want to verify that XORing them will give us the secret string. So let's see what this is. And we're going to, first of all, look at this here. And we need a property that if we have f of x1 equal f of x2, so that's what we have so far, then x2 will be equal x1 XOR s. I think that's fairly easy to check here. Now, that's an important property we have. And since we have that, let's just replace x2. Now, we're going to use, so let's name this like 1. So here we're using 1. So what we can do is move the parentheses. And now we know that this will be equal to 0. If we XOR it with s, we get s. Are you saying I have a mistake, Richard? Here? No, that's correct. All right, it's okay. But this is the answer in general. Now we can think about the classical solution. I already told you that this is what property we would be using to solve it. Now, what do we want to do? We want to find the two inputs that yield the same output. We can search for quite a long time, since we might get, for example, like this input, and the another x that will yield us 0, 0, 0 will be at the end, for example. So the very, very naive solution would be very hard as well to compute. Yeah, and it's not only for one input or one output rather, but all of them. So using this, then we can compute S finally. So we can just, the best case solution, the first occurs in like solve the problem. In the unlucky case, it will be 2 and divided by 2 plus 1. So half plus 1. Because we'll be collecting some inputs up to half, and all of them can be different from each other, can yield different outputs. And in this case, the second half has the same output. Let's say 4, 3, 2, 1. So this is why we need that many queries. Yes, there is a deterministic approach and there's a probabilistic approach that we can talk about. Now, if we introduce randomness and pick two strings randomly, x and y. So this is called the birthday paradox. I think I want to write something here just to explain it better. So the birthday paradox is a very interesting phenomenon. From, you can say, probability theory. And the paradox is that you only need how many of us are there now? 19. So we'd need 4 more people here. So that the probability that 2 of them share a birthday is greater than 50%. And that's the paradox is that you would think that it's 24, for example. It's not. And here I wanted to note that because sometimes you have a problem that's from a completely different field or branch, for example, of mathematics, but it's very similar in nature. And then if you're looking for a solution to a problem that is, well, similar, you can try to look for a similar solution. And so if we choose random strings x and y, if we finally encounter the two that we want, and we'll have to make about 2 to the n divided by 2. And because it's a probabilistic approach, it will be harder to explain, so we don't present the whole algorithm here. But there are papers that just specify the algorithm exactly. So that's a good lower bound, but it's still a lot, still exponential, which we do not want. And also exponential speedup is something that people are chasing in the field of quantum computing. So we will chase it here as well. So now we understand the problems here, and we can try our hand in doing the classical solution, seeing how it works out. So we have n equal 3, and the function, the same property that we've been studying. If we want to make random queries to f and see how many queries we made before we found our secret string s. So we want to run the procedure 1000 times and then take the average. And remember to run the cell with the oracle. That's task 3. Just to check, has the person that marked that they are working on the task still finished it? Can we proceed with the solution? Okay, great. We have our cell in the oracle. We're importing random to Python our pseudo randomness and defining just we're giving a random bit string of length n. So first thing we can do is define a function. We'll check our collision where we will get a dictionary. And now if an element will be repeated, which we want, then we found the collision. This is a dictionary, so we're checking values. So the length of this dictionary. So this line is us finding the collision, and if we found it, yeah, of course, we want to return true. Otherwise, we're returning false. Good, we have our function. So now we want to calculate how many queries we made per this question. Then let's define a list. For iteration 1,000 times. That's how many times we're supposed to repeat the procedure. We're creating the dictionary. We can, this is true. And it would probably simplify things. I will present this solution though, for now, but it is true. Now, Boolean. Now, but if we still haven't found it, we want to actually do the procedure. That's not a nice way of writing it. However, that's what we'll do. We're using the function that was given to us here. And we know that n is equal to 3, so that's what I'm putting in here. Now, we have to just continue the procedure until we have an S that has not been queried before. That's the thing with using randomness. Now our dictionary of S is equal f of S. And that means that we are using a query on F and we want to store our result in fdict, which is our dictionary. We made one more query, so that's what we will mark queries at. And we want to know what we found. So this is just checking if we just found two different inputs which yield the same output. That's this line. That will be the end of our loop here. And finally, we're appending our list with the queries we found, or rather the number of queries that we had to make. And let's do a nice print. And we have to take the average divided by 8,000. Oh, I forgot an indent, I see. Here, okay, that's right. I don't think I changed anything in this notebook, so if you got this problem, that's the only thing you need to do. And now the name random bit string. Oh, and here is another, it's called bit ring, but we want bit string. Now f is not defined.
I think we need to run the line with the oracle in the cell above.
Could you repeat?
I think you need to run the line with oracle. So one cell above.
Right, okay. Of course. We'll still have problems. Oh, it seems that just me writing things wrong. Yes, here. It's supposed to be set, not that. Of course. Okay, finally we have the answer. So the number of queries you have to make is 3 on average for our n equal 3. Seems like not a lot, but as n increases, the number of queries we have to make will increase exponentially. Let's go back to our notebook. So yes, there's a deterministic algorithm which uses commutative or abelian groups. There's surprisingly a lot of group theory if you go deep into those algorithms. And they achieve the same complexity as the best probabilistic algorithm. All right. Yes, and there's a few different algorithms that are similar. You saw that, for example, Deutsch was similar to Deutsch-Josa and Barthe-Vazirani is similar to Simon's. And it's a special class which has a definition which is based heavily on group theory, so I will not introduce it here. If you have some basis in group theory, then I recommend this article. I will link it later. So for example, but the basic thing, or if you want to get an intuition, it's if you see a function, that is that has a sort of order to it, or a period, or if it's a periodic function, then immediately you can think, oh, this has potential for solving it quantumly very fast. That's again because of the model of queries that we're making to an oracle that allows us to essentially evaluate multiple things at once, something that classical algorithms cannot do. Now, well, I think we know the problem quite well now. We understand what it is. If not, of course, you are very free to ask questions. Now, the quantum solution. So here we're going, it's an exponential speed up, meaning we go from exponential to linear. Now, again, not looking too bad. The circuit, similar. We remember earlier we just had 1, 0 here. Now we have two groups. One group of state 0. We're putting them in the plus state because we're applying Hadamard. So the bottom ones, we're not doing anything. Then we are applying the oracle. The upper ones, again, we're using Hadamard to get them back from the superposition. Then we're measuring all of the states. And let's see step by step what is happening. So this circuit has to be measured O of n times. So yes, until we have n minus 1 linear independent equations. We'll see what that means a bit later. To get a list of n-bit strings of our y's here. And then we're running the circuit. Will give us a random sample where we have this condition. All right, that's before the analysis, that's just the overview of it. So if something's not clear, I hope it will be cleared up later. So the rest of the algorithm is implemented classically. That's called classical post-processing. It's used quite often in quantum algorithms. And you can say it's part of something that's called the hybrid model of computing. So hybrid of quantum and classical computing. We measure the circuit n times, and we achieve n minus 1 equations. And what we need to do is simply solve them. So one of the solutions will be 0 to the n, and one of them will be RS. Okay. So that's for now what we'll know about the overview of it. So the general steps. First, we're doing something quantum, measuring the circuit n times. Then we get linearly independent equations. We're solving them, we get the result. Why? We'll see in a moment. So the algorithm is as follows. We already discussed it, but let's go through it again. We're applying all H gates to the qubits in the first register, applying the oracle, measuring the second register, that's here, measuring the first register, no, first applying H gates again to the qubits in the first register, then measuring them and recording the embedded string, and the strings that we get are our yi's. And we're repeating the steps until we get n-1 distinct strings y. Then we're constructing a set of equations using bit strings. Let's go through it step by step. We can already skip a little bit. Well, that's how we define our oracle. Something we already know. This will be the first register and the second register. Although I don't know how it will be called in Qiskit and in the program we'll be writing, I'm just saying in general that's how it will be. And then we want to have f of x, or y. Now our first state will just be our two registers that all start in state 0. Remember, this notation just means that we're doing it n times or for n qubits. Then we're applying the Hadamard gates in the first register, and we get a superposition. So this part is the first register. The second is staying the same. I think we remember, or this is familiar to us. It's just the superposition of state plus n times. So next we're using our oracle. And here the first register will remain unchanged as per this definition. The second one will change though. So it will produce the output values from the function f. And so that stays the same here. The sum stays the same. X stays the same. But here we have a convenient f of x. Next, we measure the second register to observe the sum of the output values. So we can say that the observed outcome is f of z for sum z. We'll be using that z later on. So now we have a couple of cases of what can happen. So if f of x is a 2-to-1 function, so when s is not just all zeros, then we'll get a superposition of the two values. So the two values that yield the same output will have a superposition. And they will produce the output f of z. So psi 3, this is where we are after the first measurement, before Hadamards, before the measurements of the first register. meaning here we'll get our superposition. This stays the same, but for some f of z. Here we have the sum of these values. And that's needed for an amplitude, so that its square is 1. The square of the sum of the amplitudes. More than the sum of the squares, sorry. Now we have a different expression, which is how can we write the Hadamard applied n times to some z. So applied to every z1, z2, etc. until zn. We're writing it in a similar way. Here, remember this because we don't know if we'll get the state plus or minus depending of whether zi is 0 or 1. And we're checking it for every n-bit string. Next, we're applying another Hadamard to transform the first register. So now we will, well, it has been measured, the second register has been measured, so we don't mind it anymore. So we apply another Hadamard, meaning we'll get another 1 divided by the square root of 2. The sum will be the same, so we can put everything under the sum. And then we'll have the minus 1 zy plus minus 1 and now zs, which is these two y's that we have. So the minus or plus responsible for what this state is in, and here it's what's responsible for this state with y. And then state y. So finally, we're measuring the first register. And now we can see that if we have the minus 1 z dot y, it will not be equal to minus 1 z xor s dot y when this term will be 0. So if this will not be equal to each other, then the sum here will be equal to 0, since one will be a minus 1 and the other will be 1. And the probability of observing y will be equal to 0. And for some y, if we want for it to have a non-zero probability of measurement, it will have to satisfy this equation. They have to be the same, so that we either get 2 or minus 2. Next. Well, since that's the case, the only way that can be true is if the exponents can have to be the same. And so they are the same, since the operation can be only 0 or 1. And now we have the property. I know it can be hard if like this operation is new to you and this operation is new to you. So if you'd like, you can check it on an example for yourself. However, that's a property that we have. It's a bit like multiplication, but not exactly, just in the way that it works in this case. So if you have z dot y, because we will be using this, will be equal to z dot y XOR s dot y. And now, finally, s dot y has to be equal 0, because here we have z dot y, and here we have z dot y. So that cannot be touched, so to say. You cannot just eliminate it or change it, because then the equation will not hold, meaning this has to be 0. Now, we have that s dot y will be equal to 0. In that case, if it's equal to 0, then the sum here will be equal to 2 and not minus 2. And we'll have a factor of 2 inside here. We'll get 2, but I will just write that we can have minus 2 because that's earlier. And now we can calculate the probability of observing y, which will be the square. So we'll have this. You can put it in front of the sum because it's just 2. And it will have to be divided by the square root of 2 to the power of n plus 1. We need to square to achieve the probability of observing y. And here's our probability. And so any string that will satisfy this property will be observed with the same probability, and strings which have the property of this resulting in 1 will not be observed. Now we have the easier case. So if s is just a 0-bit string, then we'll just obtain this state. So here we have this state. However, s is just zeros, right? So we will have z here. And so we end up with simply the state psi3 being z f of z. And we're applying Hadamard because we're just at this step right now. So we still need to apply Hadamard to the first register and then measuring the first register. What we get is quite similar. Let's see what state 4 was then. So it was much longer than that, but the structure is the same. Or yes, the structure is the same, essentially. We'll just get this because this will be equal to 0. So essentially it simplifies things a lot for us. And again, this just means that any of the states y will be observed with equal probability. Next, after measuring, we still are not sure how to recover s from that actually. But we found a string y that satisfies this property, which was important in analyzing this case. And that is happening in both cases. In the case 2 and case 1. So S can be any bit string. Now, if we make n-1 queries, we'll get many different y's, and we can create a system of linear equations so that we find out the value of S. And this is why, after we repeat the procedure n-1 times, we will get n-1 strings of y. And what we do then, we create equations like this. So simply have to apply the dot with S, and this has to be equal to 0. So this is just this property that we're using to achieve those equations for any y that we have. So if the strings are linearly independent, then we can obtain a unique solution S. And for that, approximately we need to repeat the algorithm O of n times. Now, we'll not be doing the analysis on runtime. If you have the background that lets you understand this, then you might find this interesting. Otherwise, we'll skip it. So we're already getting to the part of implementing our algorithm. We are given a black box oracle function, and it implements the function f, where s is a 3-bit string, meaning our n is equal to 3. We want to write the function Simon that will implement our algorithm. And each run will return a single bit string, y. The code that we have here, we'll call it multiple times until we have the n-1 bit strings y. So that's a simplification for us. And again, as I didn't remember to run this cell to achieve the result. We'll see. We'll have 5 minutes for that, but if some people need more time, then we'll have more time. I see more time might be needed, so I will give 5 more minutes. Unless all the people that are marking their level of completeness of the tasks will change it to completed, then we'll go ahead. Okay, 3 to 10 iterations. We'll see. We'll see. We have our registers defined, 2 quantum registers, the obligatory classical registers because we want to make measurements, and then the Simon circuit. So first, let's apply Hadamard to the first register. Next, apply the Simon oracle function. Again, barrier just for visuals. So we did this. We're applying the oracle, applying the Hadamards, and then doing the measurements. So in place essentially means we don't have to assign it to a variable. So it changes the circuit in place. We don't have to say Simon circuit equals Simon circuit compose. Just simplifying the way we write it a little bit. Doing some measurements now. So the Simon circuit. Then we didn't do measurements when applying the oracle. We just applied the oracle, but then let's do some more barriers. Then we need to perform a measurement actually on the second register. This comes first. So this measurement, then Hadamard's, then measurements. Let me take a look. Let's see. All right, we're getting 3 iterations. We had the answer of 3 to 10 iterations. Let's see. 4 iterations, 5, 3. Oh, look, we got 13. Oh, 3 is an answer very often, but I hope you got something like this. Next in the notebook, yes, we have another task. For that, we can go back to OneNote since I will be writing the solution there. Now we have obtained the list of bit strings Y from task 4, and we want to try to find the hidden bit string. So if you remember how we'll construct our equations here, this is how we'll do it. And this is what you can try doing now. And when you add S, you will get two solutions. So one solution, you will always get the S that's just a 0-bit string. And you can just discard this solution. So for this 5 minutes, this is our last task for today. We can try and see what we get. So if you run the circuit, you should see that the 2-bit string that we're getting are 100, 101, sorry, and 001. Now, how do we construct the system of equations? We'll be simply using this property. And here, S is S1, S2, S3. So, S dot 101 is equal to, we can only get, do you remember common ones? So here we cannot get a common one, so this will be 0. Here there is a chance, meaning it will be S1 from this plus S3. And this has to be equal to 0 modulo 2. Similarly, with 001, give me a second. Well, we will get 001 is equal to S3 equals 0 modulo 2. And then we just solve it. So here S3 is equal to 0. Meaning S1 has to be equal to 0 as well. Right? Because this will be 0, so this has to be 0 modulo 2 as well. And now S2, we didn't have anywhere in here. So it can be either 0 or 1. That's our solution. And so now we have two options, 0, 0, 0 or 0, 0, 1. Or sorry, no, 0, 1, 0. Since that's S2. But this is a 0 solution, so we're discarding it. And so finally, that's our S. That's the solution. I hope you got something similar. And this marks the end of the conventional quantum algorithms part. So to summarize, we learned something first of all, how to represent classical gates in a quantum way, where we saw that all of classical computation can be simulated quantumly. Then we learned about phase kickback, which is a very important phenomenon used in several quantum algorithms when the eigenvalue is kicked in front of the state. Next, we learned Deutsch algorithm, which was a toy example because it simply was 4 possible functions. So you cannot get any significant speed up, but this demonstrated well how the oracle system works, how our functions, which is the hidden subgroup problem, how they function, and that it proved finally that we can get an advantage, even if it's not maybe, let's say, computationally significant. It's still an advantage. So in classical gates, we saw that all classical computing can be simulated quantumly. And now we see that there's something more in the quantum way, so we can do more things in a quantum way. That's an important thing from this notebook. Next, we generalized Deutsch algorithm in Deutsch-Jossa, where we did have finding n-bit strings, so the speedup was more significant. However, the method still had some caveats and wasn't, again, it isn't as significant. However, it's a good example of, let's say, generalizing algorithms using the same methods. Then we learned about Bernstein-Vazirani, where we were looking for the secret string, something we're looking for in Simon's algorithm as well, using a similar model of computation for a different problem. And finally, Simon's algorithm, which is a significant algorithm. It provides exponential speedup with regards to the classical counterpart. And it has been an inspiration for arguably the most important quantum algorithm, which is Shor's algorithm. And next, we'll be doing something that is very significant. And we'll see how we can apply these types of oracle-based algorithms to real problems which are, let's say, physically speaking about, let's say, the outside world. They are significant, and I hope that will be interesting for you. Okay. Are there any questions? If not, then I will thank you very much for today. And I hope to see you tomorrow. It will be graph theory. I find it quite interesting. I hope you will too. So, good night, everyone. I hope you have a good evening.
Thank you very much and have a good night.
Thank you.
Thank you very much.
Thank you. Bye.
Thank you. Goodbye. Dobranoc.
Dobranoc.